Dear students, in last class we derived an expression for capacitance of a capacitor to improve the power factor of an RL circuit from cos phi 1 to cos phi 2, and also we solved few problems there. In today's class I will start with next chapter, that is three phase circuits. In three phase AC circuits, three phase sources are used to supply three phase electrical circuits. So now let us know what are three phase voltages. Three phase voltages are produced by rotating a three phase winding in uniform magnetic field. As shown in figure below. Now in this figure you can see three windings, namely R, Y and B, where R stands for red, Y stands for yellow and B stands for blue, spaced at 120 degree to each other, are placed in the uniform magnetic field produced by the two poles N and S. Now if this winding is rotated in the magnetic field, then the flux linking with all these three windings will go on changing with time. Therefore, EMF will be induced in these three windings. And what type of this EMF induced is? The EMF induced here is dynamically induced EMF, because there is relative motion between the windings and the magnetic field. The EMFs induced in these three windings are 120 degree apart from each other. That means the EMF induced in each of these coils will be crossing the omega t axis with a delay of 120 degree, one after the other. Now we can write the expressions for voltages so obtained in these three windings. Voltage is obtained from a three-phase generator. Generator means what here? Source. Or sinusoidal in nature. But 120 degree apart from each other. These voltages are given by VR equal to Vm sine of omega t Vy equal to Vm sine of omega t minus 120 degrees and Vb equal to Vm sine of omega t minus 240 degrees. Now look at this figure here. Let us say this is our reference line, that is 0 degree. While rotating these three windings in the uniform magnetic field, R winding will cross this reference first and then Y winding will cross the reference. After Y crosses the reference, 120 degree later, B winding will cross the reference. In other words, we can say after R crosses the reference, 240 degree later, B winding will cross the reference. That is why we have written here three voltages as VR equal to Vm sine omega t, Vy equal to Vm sine of omega t minus 120 and Vb equal to Vm sine of omega t minus 240 degrees. And these three voltages induced in three windings are called as phase voltages, and the three windings are called as phase windings. Voltage induced in R winding is called R phase voltage. Voltage induced in Y winding is called Y phase voltage. Similarly, voltage induced in B winding is called B phase voltage. Now we will draw the waveforms for these three phase voltages. Along x-axis I will take omega t. Along y-axis I will take instantaneous values of R phase voltage, Y phase voltage and B phase voltage. Now this will be our R phase voltage. So now we have completed drawing the three phase voltages. Just name this as Vy and the third voltage as Vb. Here once again you will be having Vr. If you continue with Vr, you can see that after Vb, Vr once again appears. I will mark the omega t values at different instants. Here it is pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, 2 pi, then 7 pi by 3, 8 pi by 3 and so on. And here you will see the positive peak voltages Vm, Vm, Vm and Vm. Next we will define what is phase sequence. Now look at these waveforms once again. Here you will find R phase voltage reaches its maximum value first. Then Y phase voltage reaches its maximum value. After that B phase voltage reaches its maximum value. After B, once again R phase voltage will reach its maximum value in the positive direction. So, the order in which the instantaneous voltages reach their maximum values is called as the phase sequence. So, here phase sequence is R, Y, B, or you can say Y, B, R, or you can say B, R, Y. Phase sequence. It is the order in which instantaneous three-phase voltages reach their maximum values in the same direction. In the figure above, RYB or YBR or BRY is the phase sequence. Necessity of three-phase systems. Three-phase systems are necessary because of their advantages. Three-phase systems are very much necessary comparing to single phase systems. Because of the following advantages. First one, cost of transmitting three-phase power is less comparing to single phase power transmission. Second one, for same power rating, three-phase generators motors and transformers are of small size comparing to single phase generators motors and transformers of same power rating. Here comparison is made between three-phase machines and single-phase machines on the basis of power rating. Third advantage, all the industries use power in bulk. Industries use power in bulk. It means that they make use of large quantity of power comparing to domestic consumers. Supplying power to industries with three-phase systems is cheaper. Fourth advantage, industries use three-phase induction motors which are self-starting. Whereas single phase induction motors are not self-starting. Fifth advantage, three-phase motors develop higher torque comparing to single phase motors. Sixth advantage, cost of three-phase motors, generators and transformers is less than that of single phase motor, generator and transformer of same ratings. Seventh advantage, three-phase motors develop uniform torque whereas single phase motors develop non-uniform torque. Eighth advantage, three-phase motors and generators are quiet in operation. That means noise produced by these three-phase motors and generators is less comparing to the noise produced by single phase motors and generators. Ninth advantage, three-phase systems are efficient. Next we'll take up types of three-phase systems. There are two types of three-phase systems. based on connections, and they are: first one, star connected system, and second one, delta connected system. Now we will see these two systems in detailed. First one, star connected system. In this system, connections look like capital letter Y, common point is called as neutral. First we will show three-phase generator whose three windings are connected in star. And then we will show three-phase load in which three loads are connected in star. Each winding in case of generator is connected to a common point, and that common point is called as neutral. Similarly, each load is connected to a common point, and that common point here is also called as neutral. The free terminals of generators are connected to the load. The conductor that connects generator terminal to the load terminal is called as line conductor. And winding in each phase is called as phase winding. Similarly, in case of three-phase load also. Conductor that connects load to the three-phase source is called line conductor. Impedance in each phase is called as phase impedance. So I will write here three-phase star connected generator, and here I will write three-phase star connected load. Next we will see delta connected systems. In this system, connections look like delta. Neutral point does not exist. In delta connected systems. Again, here also I will show you delta connected generator and delta connected load system. Like in case of star connected systems, here also you can see the line conductors. Phase winding. And phase impedance. So it is three phase delta connected, generator, and here it is, three phase, delta connected, load. Dear students, in next class we will study the definitions of line current, phase current, line voltage, phase voltage, and also we will derive the relationship between line and phase voltage in case of star connection and line and phase currents in case of delta connected system. I will stop the class here. Thank you.